Okay. So now here we saw that we have different types of unit cells, right? We have a primitive unit cell, we have non-primitive, in which we have face center, body center, and we have end-centered unit cells. End-centered unit cell. Exams are starting from 8th May. Which examinations is there?
So PT1, yeah.
PT. Which chapters are there in that examination?
Solutions and haloalkanes, that chapter in part two.
So one first thing is that, see, you have to try to now deal with those like small examination for PT now, because we are mainly aiming for two main things, है ना? The entrance examination that you have, है ना? And the 12th board.
Yes.
Okay. So after Eid, we are going to also classify the batches into three categories. We will have a batch on CBSE only. That means we will be just solely focusing on board examination. There will be a batch for JEE, and there will be a batch for the NEET. Okay, so these three batches will be there. Now again, in CBSE, JEE, and NEET, we can't really focus in any of these. We can't really focus on, I can say that, the PT questions, like the periodic tests, right? Because if I focus on periodic tests, then what is going to happen? If I prefer periodic test, then आपकी स्कूल में कुछ chapters हो रहे होंगे, बाकी schools में कुछ दूसरे chapters हो रहे होंगे, है ना, exam test में. This is going to be confusing, है ना? So we'll be mainly dealing with the board examination जो होने वाला आखिरी में, because उसी का marks जो है आपके पास आएगा, है ना, 12th standard में. You don't have any contribution of these periodic tests, right? ज़्यादा नहीं था, है ना? ठीक है, तो our focus will be on the board examination. You have seen the movie Race, or have you not? No.
So can you repeat, please?
Race, yeah, of Shah Rukh Khan.
No.
There is one dialogue in that. The dialogue is like, "Mohalla bachate bachate shahar jal gaya." You understand what does this mean?
Yes.
Mohalla bachate bachate.
On concentrating small things, we destroy big.
Got distracted from the bigger picture. ठीक है, तो वो नहीं करना है ना? तो try on your own. Solutions हम लोग start कर देंगे, ठीक है? I think अगर कल आपकी क्लास हुई तो कल ये चैप्टर खत्म हो जाएगा बिल्कुल, और फिर नेक्स्ट क्लास से सॉल्यूशन स्टार्ट हो जाएगा. लेकिन मेरा हम लोग का फोकस मेन बोर्ड एग्जामिनेशंस पे होगा, ठीक है? अच्छा, now looking at things, we have primitive, we have face centered, body centered, and end centered. All of these are parts of non-primitive, right? And also we have learned that there are 7 crystal systems. Seven crystal systems. Okay. Now, this 7 crystal systems are there, and there we have all of this. Let's say cubic, for example. So cubic can have one primitive, it can have one face center, it can have one body center, it can have one end center. Okay. Now, if you see, let us say tetragonal. So tetragonal can also have 4 different types of unit cell. Now, essentially, theoretically speaking, we should have 7 crystal systems. Each of them is having 4 different type of unit cell, and there should be in total 28 lattices. Yes or no? Do you understand this point?
Yes.
And there should be 28 different ways in which we can arrange the points, and 28 different ways. But we also know that when we arrange the points in the triangular fashion, and when we arrange the points in the parallelogram fashion, both of these were essentially meaning the same thing. Yes or no?
Yeah.
Both of these are same, right? And that is why there will be some kind of duplicates in this 28. Okay, and how many are they, and how we can distinguish between those 28? It is very complicated, and it is also not there in the syllabus. And it is the अच्छा ये बताइए, chemist तो काम नहीं कर रहे हैं इस पे, है ना? The chemist people, they are not working on how to arrange points. Who will be working? Physicists काम कर रहे होंगे. Physicists काम कर रहे होंगे नहीं. Mathematicians. This is basically not geometry, na? Basically this is geometry, right?
Yeah.
So basically we have mathematicians who deal with this stuff. Okay. And so Auguste Bravais, French, है ना? Auguste Bravais, it is written as Bravais, but it is Bravais. He mathematically proved that there are 14 distinct ways to arrange point space. Now, what are those and how are those? You don't have to remember, but you have to remember this word, that there are 14 distinct ways. Okay, there are 14 distinct ways in which you can arrange the points in a space. Okay, and these are known as 14 Bravais lattices. 14 Bravais lattice. So the question that you can be asked is, how many Bravais lattices are there? And in how many ways can we arrange points in space? If you want to look at these 14, then you can refer to NCERT, and the page number is 11th page number of the first chapter. Okay. Now moving on, we have this 14 distinct ways, and each of this lattice points, and if you have watched the lecture or if you have been in the class, then you will remember that we discussed about crystal lattice in one of those classes. Crystal lattice, right? Crystal lattice, right? So crystal lattice is the arrangement of points, and these points represent atoms. So it is basically the 3D representation of atoms in space, and each point it represents an atom or we can say constituent particle, because we know the constituent particles can be ions also, it can be molecules also, right? So each point in the crystal lattice represent one constant particles. Okay, now moving on.
Yes.
A few things regarding unit cells. Now these are just you can say trivia knowledge about unit cells, that generally the unit cell which has perpendicular sides, those are chosen. So you can see that this can be also chosen and this can be chosen. Generally this is excluded. Okay, if you have a choice, then this is a unit cell. Again, the word chosen means what? The chosen words means all of these are unit cell, but we have to choose one of those. We essentially chose this one, if you remember, for square close packing, and this was due to the coordination number, right? This was due to the coordination number. Okay, now this is again trivia, don't have to remember it. Now at last, I want all of you to tell me in chat, what is this unit cell? What is the name of this unit cell? What is this name? You have atoms in the corner. It is a cube. So obviously it is going to be primitive. First of all, primitive. But in primitive, what is this unit cell named? No. ये तो 2D में होता है ना? नहीं, ईशान फेस में कहाँ है? ईशान फेस में तो नहीं है कोई atom. Why are you saying FC? Yes, ईशान. Are you saying face centered? फेस में तो कोई atom नहीं है. No. Unit cell. नहीं तो आप लोग रिवाइज नहीं कर रहे हैं. प्लीज रिवाइज. ओके ईशान, दिस इज सिंपल क्यूबिक. और जो सीसीपी आपने लिखा है ना, सीसीपी जो होता है क्यूबिक क्लोज पैकिंग, दैट इज अ पैकिंग, नॉट अ यूनिट सेल. ओके, दिस इज बॉडी सेंटर्ड क्यूबिक, बीसीसी बॉडी सेंटर्ड क्यूबिक, and this is FCC, that is face centered cubic. And FCC का जो पैकिंग होता है ना, if you arrange all the atoms, so this is a packing, right? This packing is known as CCP. The packing of FCC is known as what? It is known as CCP. Okay, and FCC is the unit cell of cubic close packing. Okay, is that clear? Yes or no? Please tell me.
Yes, sir.
Okay. No.
Yes, sir.
So this is the end of the classification of crystal lattices. We have last thing, which is the imperfections in solid. Okay, imperfections in solid. So let me open the slide for that also. Imperfections in solids. Whenever you have imperfections, there will be something which is ideal. Then only you can compare the remaining real things and see where are the imperfections. So what is an ideal solid? You can be directly asked, what is an ideal solid? So an ideal solid, it will have the same unit cell, and this unit cell will be containing the same lattice points. And lattice points means essentially atoms, same atoms. Okay, throughout the whole crystal. So it means that each of the point will be like this. So let us say if I start here and there is distance D, D, and in the 10th D, I find one atom that is in red color. Then I can expect and predict that even if I go 1000 D and 1000 distance away, then also I will be getting a red atom. So this is a type of ideal solid in which you have the same unit cell. It contains the same points or atoms that is present in the whole crystal system. Now, if you have any deviation, that is known as imperfection. Okay? If there is any deviation, मान लीजिए आप you are going like this, red, 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 and in between you get, let us say, some yellow atom here. Okay, now this is what? This is an imperfection, right? This is an imperfection. So if there is any deviation from the completely ordered arrangement of constant particles in a crystal, this is known as disorder or defect or imperfection. Okay, this is known as imperfection. Is this clear? Ideal solid and there are imperfections. Okay, so ideal solid means you will have same atoms in the unit cell throughout the whole crystal, and imperfection will have some kind of deviation. Now we are mainly focused on this imperfection part. We have to look what are the different kind of deviation that can happen. Now there can be point defects. Now this point defects means that there will be deviations around a point. For example, just as I said, red atoms here, and suddenly you found that there is no atom here, and then after that you have some atoms present. So this is a point defect because you are having a deviation. You are having a deviation around a point only. Other thing that can happen here is that if you have red atoms like this, and suddenly you found that there is a yellow atom in between, and furthermore there are again red atoms there. So again, this is also a defect because we are expecting red atoms, but we are getting a yellow atom here, and this is also restricted around one atom. And that is why it is known. These type of defects will be known as point defect. Okay. Now another type of defect is line defect. Now line defect will have the arrangement of the whole row of atom will be disturbed. Okay. So if you have red atoms like this, okay, we are having red atoms here also. We expected red atom here also, but here there are some red atoms. Okay, then we had a range of yellow atoms like this. So if you have this kind of defect, then it is going to be known as the line defect. And we are not going to study line defect. This is not we are going to study. We are just interested in point defect because these are easy to distinguish. Line defect is there in higher studies. Okay, you don't have to deal with line defects in this class. You just need to know the definition of line defect, that irregularities or deviation from an ideal arrangement in the entire rows of lattice point. It is known as line defect. Okay. Now further moving on to point defects. Now this is causes of point defects, and it is only for non-ionic crystals. Okay, non-ionic crystals. It is basically in two types. There is interstitial and there is vacancy. Now in both the cases you can see that there is interstitial defect, and here there is vacancy defect. Interstitial defect, what is happening? There is a foreign atom which is occupying the interstitial site. Foreign atom which is occupying the interstitial site. Essentially, it should have been like this. Essentially, it should have been like this. This should be completely vacant, right? You should not have anything there. This should be completely vacant. Okay, but you have a red atom here, right? So it was initially a void, and voids are also known as interstites, right? Interstitial points, right? So these are interstitial points in which you should be having voids, but there are atoms, some foreign atom present here. And that is why these are known as interstitial defect. Vacancy defect, as the name suggests, there is no atom present here. There is no atom present here. Okay, now let us see the consequence of this. The first thing is that if you look at the ideal crystal, here, then ideal crystal will have 20 atoms. Yes or no? 1, 2, 3, 4, 5, and here you have 4. So ideal crystal should be having only 20 atoms in the pattern. Yes or no? Correct?
Yes, sir.
And let us divide this by the volume, whatever volume is present. Now, if I look at the deviation, that is the ID, that means interstitial defect is having 22 divided by the same volume. Now you tell me which is having more density, ideal or the defect one? Ideal or the defect one?
Defect or defect.
Defect piece will be having more density. Okay, so that is why in interstitial defect, the density increases. And here you can see that the ideal will have 20 upon V, but the defect is having how much? 2 are excluded. There is vacancy here. So it is having 18 atoms divided by the volume. And in this case, the If you have vacancy defect, then the density decreases. Density decreases. Okay, so these are the 2 points that you have to remember. This is the definition here. You will write that. Here is the effect. Now, in this, you have 3 points. The third point is just saying that this can be done. You can have vacancy defect by heating, and that is why it is also known as thermodynamic defect. Please remember, this is very important. Okay. It's important. Now, last thing that you have to remember is about the non-ionic solids are only showing vacancy and interstitial defects. Okay, so these 2 defects are only for, please remember, only for non-ionic. Only for non-ionic crystals or non-ionic solids. Only for non-ionic solids. Okay, so these are 2: vacancy and interstitial. Density decreases in vacancy and density increases in interstitial defect. Moving on, the point defects in ionic crystals. Okay, so we have to only learn the point defects. Now we have classified the solids into non-ionic and ionic. Like when we are studying defects, we have seen the non-ionic crystals and what are the defects shown by them. Now we have the ionic crystals and their defects. So the first is stoichiometric defect. Second is non-stoichiometric defect. And the third is impurity defect. Okay, so stoichiometric defect, non-stoichiometric defect, and impurity defect. So in stoichiometric defect, the ratio of positive and negative ions is same as the ideal crystal. Okay, the same as the ideal crystal. In non-stoichiometric defect, the ratio is not same. The ratio of this positive and negative ions is not, okay, is not same as ideal. ठीक है, देखिए अब हम एग्जांपल देते हैं आपको. Stoichiometric defect. In stoichiometric defect, for example, if I have NaCl now, so NaCl में what is the ratio? For each Na we have 1 chlorine, right? In NaCl, for if you have 3 Na positive, then you will have 3 Cl negative also. If you have MgCl2, then the ratio is what? 1:2. Ratio is 1:2. And for each Mg you have 2 chlorine. But if you have, no, this ratio will be preserved, it will be conserved if you have stoichiometric defect. But if you have non-stoichiometric defect, then you will be having formulas which will get reflected, and you will be having such as, you will see this problem: nickel 0.98, oxygen 1. You will be having this type of, so for each, you can say for each 100 oxygen there are only 98 nickel. But the ideal crystal it had NiO. Okay, NiO, nickel oxide. So in ideal we had for each 100 oxygen there were 100 nickels. But in non-stoichiometric defect, when you have non-stoichiometric defect, then you are having only 90. We will look at this in detail. I'm just saying what are the difference. Now in the impurity defects, there is foreign ion present in crystal. So these are the 3. Stoichiometric, the ratio is preserved. Non-stoichiometric, the ratio is disturbed. Impurity, we have some foreign. So let us first of all look at the stoichiometric defect. Now, stoichiometric defects are 2 types: Schottky defect and Frenkel defect. Let us look at Schottky. So what do you see here? In Schottky, which atom should be present here? Tell me now. The red atom or the blue atom?
Red atom.
Red atom. And here there should be a blue atom. Yes or no?
Yes.
Correct. Yes. Now, you can see we are missing 1 red atom and 1 blue atom. Right? So if I am removing 1 sodium, then we have to remove 1 chlorine also. Correct? You can see that the stoichiometry is maintained. As an EK, we have just removed 1 sodium atom. And if you just remove 1 sodium atom, then what is going to be having? You will be having more chlorine. So the ratio will be disturbed. So in stoichiometric defect, we don't do that. For each positive, we are removing 1 negative also. For each sodium, there is 1 chlorine that is getting removed. Okay, so Schottky defect, in this, you can also say that Schottky defects, what is happening? Ions are getting short. So you are missing some ions, and that is why it is Schottky. In Frenkel, what is happening? There should be some atom present here, that is the orange or red atom, and it has moved from its place and it has gone to this interstitial site. Now what is happening? This ion, sodium ion, it is very excited and he wants to make more frank. That is why it is more frank. Okay, so ions are getting frank. So if ions are getting frank, you will remember that it is Frenkel defect. Now you don't need to remember now the definitions. You see the picture, you remember this term: ions are getting short and ions are getting frank here. Ions are getting Schottky defect. Ions are getting Frankel defect. You remember these two pictures and you will write on your own what are Schottky defects and what are Frankel defects. Okay. Now, what is the consequence of Schottky defect and Frankel defect? First of all, it's the density. So in density, as you can obviously see, what is happening in Schottky, you are having some atoms which are getting removed. So some mass is getting removed. If the mass is getting removed, that means the density will decrease. In Frankel defect, you may say that, sir, yahan bhi hai. Here also we are having some whole atoms are missing, but no. The atoms are moving, they are inside the crystal only. So the mass is not going to decrease. So density remains same. Density is same. Now, we can also talk about the electrical conductivity here. Okay, electrical conductivity. See, if you have this hole here, and if I have an electric field, then the charge will move. So what is going to happen? This red atom, it will come here, and a hole will be produced on this side. Then this will come here, and the hole will be produced this side. So you can see there is a movement of ions that is facilitated by a hole, and that is why there will be an increase in electrical conductivity. So electrical conductivity increases. And here also you can see that this chlorine atom can come here, there will be a hole here, this chlorine atom can come here, there will be a hole here, then the further chlorine atoms can come. Similarly, here sodium atoms can move this side, right, like this. And you can see that charges are moving, and that is why the electricity is being conducted. So in both the cases, the electrical conductivity will increase. Now let us look at the strength of these crystals. So the strength of ionic crystal is defined by lattice energy. Lattice energy is the energy required to break these. Lattice energy is the energy required to break the ionic crystals, Now, since we have holes in both the cases, in Schottky defect also, in Frankel defect also, we have holes here. Now, if hole is present, that means there is some mass that is not present, and that is why it will be a bit easier to break these type of crystals in which we have holes. Okay, so the lattice energy is going to decrease. We need to give less amount of energy in order to break this type of crystal system. So is this understood, everything about Schottky defect and Frankel defect? Yes or no, please tell me. About density, about electrical conductivity, and about the lattice energy. Yes, Zaid and Ishan.
So can you explain the last part again, about lattice energy?
You know what is lattice energy, Ishan?
The energy needed to break between the two atoms.
No, not between two atoms. The energy required to break 1 mole of ionic crystal. Okay? Okay,
sir.
Anna. So now you are having some holes here. Na? Since you are having some holes, there will be some attractive forces which will be missing. यहाँ पे अगर देखिए chlorine होता, there will be chlorine here, then there will be attractive forces between the sodium atoms like this, which is not present. And that is why these are not having the ideal attractive forces, and that is why it will be easier to break them. Obviously, you think about it. Now, if you have hole in solid, then it will be easier to break it. Yes or no?
Yes.
I know. Okay. So whatever I have explained, those things are present here in the consequences of. Okay, this is again the same thing. The differences I have put here. If you get a question on differences, Schottky and Frankel. In this case, you have both the atoms are missing, and this is the density. And as you can also see, one more thing from explain. In this case, in Schottky defect, what is going to happen now? If you have the positive and negative ions, which are, if they are of similar sizes, then the Schottky defect will be there. Because if you are removing something, both are of similar size, then they can be removed easily. In Frankel defect, what should be there? The negative charge should be larger and the positive charge should be smaller. So if you have larger negative charge and smaller positive charge, it will be easier for the positive charge to move here and there. Okay, so that thing is there in the last point. So last point, you have an ionic crystal which have high coordination number and in which we have cations and anions of equal sizes. In Frankel, what should be there? It should be the anions are larger in size than the cations. Anions are larger in size than the cations, in which you will show Frankel. I will give you one question. Which ionic crystal shows both Schottky and Frankel defect?
Sir, is it AGBR?
It is AGBR, correct. It is AGBR which shows both. Okay, shows Schottky and it shows Frankel also. Okay, moving on. The consequences we have discussed: electrical conductivity increases due to presence of holes in the crystal, the density decreases, and you have to remember that only for Schottky defects the density is decreasing. Next is the presence of holes. Now, if the presence of hole is there, then lattice energy or the stability of crystal is decreased, and due to presence of many holes, the partial collapse. There is some partial collapse in the lattice. Okay, so it is not ideal. And the last point is about the dielectric constant. You have to remember this. Okay, the dielectric constant is what it increases in Frankel defect because you have seen here that you have 3 positive charges in the same side. Positive, positive, positive. If you have this type of arrangement, then the dielectric constant increases. That means the electrical permeability increases here. Okay, that is the last point. Due to the closeness of similar charges in Frankel defect, it tends to increase the dielectric constant of the crystal, the electrical permeability. So electricity moves here in this Frankel defect very easily. Electric field basically. Okay, so moving on, we have discussed the point defects, that is stoichiometric. Then we have non-stoichiometric defect. Okay, so before doing non-stoichiometric defect, let us write this question. Please all of you write this question now. You will understand the non-stoichiometric defect more effectively by this question.
So nickel will only change here. Oxide will remain same here.
Oxygen is 1. Done writing the question, yes or not, Amy?
Yes, sir.
Okay. So we have here nickel 0.98, oxygen 0.00. Now the questioner is asking what fraction of nickel exists as Ni2 plus and as Ni3 plus. So they are obviously saying that in this nickel, this nickel, you have 2 types of nickel. You have one nickel which is Ni2 positive, and you have one nickel which is Ni3 positive. Okay. Now we have this oxidation state +2 and +3. What will be the oxidation state on oxygen? Tell me. Oxygen में क्या होता है generally? Oxidation state of oxygen is what? -2, right? Yes or no?
Yes, sir. O2 minus.
Okay. Now you have a set of cations. You have a set of anions. And I will say that whatever the charge of cation is there, and whatever the charge on anion is there, they both should be equal in magnitude, not in sign, equal in magnitude. Yes or no?
Yes, sir.
Correct? Okay, fine. Now we will start from here. That is the electrical neutrality. Okay, this is the main thing. Electrical neutrality should be maintained. So let us say in that I should say for each 100 oxygen ions, there will be 98 nickel ions. Yes or no? Correct. We are not interested in what type of Ni2 plus or Ni3 plus, but I can say there are 98 nickel ions as the formula is suggesting, as the formula of solid is suggesting. So I will write, let us suppose let Ni2 plus is equal to X. Okay, we have X amount of Ni2 plus. Then the amount of Ni3 plus will be how much? 98 minus X. Yes or no?
Yes.
Correct. Okay. Now let us see the charge on anions. So we are taking 100 oxygen. So there is -2 charge, but I'm just taking the magnitude of charge. Okay, magnitude of charge will be equal na 200 200 dono 2 into 100, which is equal to 200. This is the charge on anion. Then the charge on cations, let us see. The charge on cations. Charge on cations will be C. This is X. Now, there are X number of N2 positive, so there will be X into 2. This will be the charge of Ni2 plus, and the charge of Ni3 will be plus 3 charges there, so it will be 3. Let me remove this. There will be 3 and 98 minus X, right? Now, I know that the charge of anions and cations should be equal, so this should be equal to 200, correct? Now, if I simplify this equation, you will be getting 2x plus 98 3 is 294 minus 3x, which will be equal to 200. Okay. Now, if I move this here, so this will be minus 3x plus 2x. So this will be equal to x minus x, sorry. And here you have 294 going there, so it will be minus 94. And hence you can write x is equal to 94. Now, if x is equal to 94, then 98 minus x, it is equal to how much? 98 minus 94, which is equal to 4. So I will say now fraction of Ni2 plus is equal to how much? See, we have 94 nickel 2 plus out of 98 nickel ions, and the fraction of Ni3 plus, it is equal to how much? There are 4 Ni3 plus in each 98 Ni ions. So do you understand this whole problem? Yes or no? Please tell me.
Yes, sir.
This is the most important part of the question. Okay, this is the most important part. Charge on anion should be equal to the charge on cation. All the charge cations, if I add them, they should be equal to the total charge by anions. Okay, this is the most important point. Okay, so now you understand in stoichiometric defect what happens. There is a crystal in which we have 100 oxygen and 98 nickel. Okay, so what is excess here? We have more metal or less metal? We have less metal atoms, right? So this is metal is deficient here, right?
Yes.
Metal is deficient here. Okay.
So finished.
Now, let us look at the types of non-stoichiometric defects. Okay. Non-stoichiometric defect, what is the definition here? Definition is the thing that we have said, the ratio of positive and negative ions present in the compound differs that required by the ideal chemical formula of the compound. These compounds are known as non-stoichiometric defect, and the defect that will be present, it will be known as non-stoichiometric defects. So compound are non-stoichiometric, and the compound is non-stoichiometric, and the defect in them, it is known as non-stoichiometric defect. Okay. Now moving on, we have non-stoichiometric defect, which are divided in two types: metal excess defect, metal deficiency defect. Okay. So metal excess, that means more metal, and metals, these are generally cations, nickel 2 plus Ni, sodium, all of these metals, they are always cations in ionic crystals. So what I can do, if I want more metal, then I can remove anion by doing some anion vacancies. We are removing anions, or what we can do, we can add some extra cation. So these are the two ways in which we can have metal excess. Metal deficiency ke liye kya karna padega? We can remove the metals, that means cations, or we can add some extra anions. Okay, so we have two defects: metal excess defect and metal deficiency defect, which can be caused by two of different categories in each of them. Yes or no? Is this clear?
Yes.
Okay, now moving on. Next we have the metal excess defect due to anionic vacancy. Here we are creating some anionic vacancy. So the name suggests what we are doing. Now we are removing the anion. So we are removing this anion here. But the question is always like, how is the charge stabilized? How is charge stabilized? Okay, so you'll be looking at the charge, how it is stabilized. So when we are having metal excess defect due to anionic vacancy, then we are adding some electron. So electron is trapped here, and this electron is maintaining the charge. Please remember, we should be having B negative in the ideal crystal, B negative. So B negative is not there. We can remove B negative. Yes, of course we can remove the B negative, but we have to give it the charge also, right? We can remove the B, no problem, but we cannot remove the charge now. If the charge is removed, then the molecule will be charged now. If you touch it, you will get shocked. So in nature, you don't have anything which is unstable, which is charged. You have everything. Most of these things are what? These are stable. And that is why you have an electron, which is stabilizing it, which is stabilizing the whole crystal. Next is this charge, this electron, what it can do, it can absorb some light. And if it is absorbing some light, then it is reflecting some of the wavelength. देखिए white में क्या होता है? Absorb होता है ना? And let us suppose this electron is there, and it is only absorbing this part and getting into higher state. Then it will be reflecting green, yellow, orange, and these are the colors that you are going to see. Okay, these are the colors that you are going to, the mixture of these colors that you are going to see. Okay, now these centers are known as F centers because they impart color. If you have any of this electron here in vacancy, in anionic vacancy, these are going to give you some color. Okay, next is due to extra cation. In extra cation also we are adding cation. We are adding positive charge, so we'll also have to add some negative charge. So what we are doing, we are adding electrons here. We are adding electrons here. Okay, so please remember this is known as F center. This is not known as F center. Okay, so the electrons trapped in anion vacancies are known as F centers. Okay, next is the constant. Okay, again, same thing. The consequence of the metal excess defect will be that it will conduct electricity. Why? Because in both the cases, you can see that there is free electron here. So if free electron is there, that means you will be having some flow of electrons and the electrical conductivity will be there. Moving on, we have another thing, which is the color compounds. Okay, so metal excess defects are generally colored. The examples you will always be asked like this: why is sodium chloride sometimes yellow? Why is potassium chloride violet? Why is lithium chloride appears to be pink? So all the answers will be that they are having metal excess defect. They are having metal excess defect. These are the consequences. So we just saw that metal excess defect. Okay, then we have seen these two things: anionic vacancy and the presence of extra cations. Now let us look at the metal deficiency defect with cation vacancy and presence of extra anions. First of all, cationic vacancy. So we are having cationic vacancy. If cationic vacancy is there, then what is going to happen? If cationic vacancy is there, then means your metal is acquiring a higher charge. जो हो रहा था आपके nickel oxide में. So nickel was 0.98, oxygen was 100. So obviously there was some less nickel. So this was deficiency. And if there was deficiency, then what was happening? In the crystal of Ni2 positive, there were some atoms which are gaining a higher positive charge, that is of Ni3 plus. Yes. So this is an example of metal deficiency defect due to cationic vacancy. So how are we stabilizing the charge? By metal acquiring higher charge. In the previous case, when we had metal excess, there we added electrons. Here we are increasing the charge. On metal. Increasing the charge on some ions of the metal. We can say not all the ions, but some ions. Okay. Now due to this hole here, these B electrons, these can move here, right? These can move like this. Now, if they are moving, it produces some lustrous kind of sign, and that is why these are sometimes known as fool's gold. They appears to be gold, but these are not gold. Okay, so in this line, I have just written why it is, how it is getting stabilized. Okay, this hole, how it is getting stabilized. You will get that in the PDF, and I will send you. Now moving on, next we have the metal excess defect due to extra anion. Here also, if you add extra anion, we are going to stabilize this by the metal acquiring a higher charge. So metal is acquiring a higher charge, and we are stabilizing this extra anion, which is on the interstitial side. Okay, so these things you all please remember. You can also be given this type of system crystal, and you'll be asked what type of defect is present here. Okay, so again, this is again the explanation how are the charges stabilized. Again, the explanation how are the charges stabilized. Okay, so we have discussed metal deficiency, and we have also discussed metal excess defect. So in deficiency, we can have two things. We can either remove cations, so cationic vacancies can be there, or we can add anions. Here we can remove, or there can be anionic vacancy, and what can we do? We can remove, or we can add metal excess. We can add metals, right? We can add metals. So these are the two things we can do in both the cases. Now the last thing is the impurity defect. Again, for impurity defect, you write this question. Okay, this will give you a better idea of impurity defect.
Sir, I think doping is removed from this syllabus.
What is removed from the syllabus?
Doping. Dop.
The whole chapter is removed from the syllabus now.
Yeah.
Correct. But still we have to do this, right?
Hmm.
Done?
Yes, sir.
Done writing the question, yes or no?
Yes, sir.
Okay. Now let us see NaCl. NaCl is doped with this much of SrCl2. पहले देख लेते हैं what happens if you dope NaCl with SrCl2. That means you have NaCl crystal. Na will be there. There will be Cl. There will be Na. There will be Cl. There will be Na. And here you will be having Cl. There will be Na here. There will be Cl here. Na here. Cl here. Sodium chloride. Sodium chloride. Sodium like this. Okay. Now let us suppose we are adding only one molecule or one molecule of SrCl2. So one thing I can easily see that this Cl2 is not going to affect any of this crystal because here also we are having Cl. Yes or no? Tell me.
Yes, sir.
Yes, sir.
We are also having Cl, so it is not an impurity here. Cl is also already present in it. But the strontium ion is a different thing. Strontium ion is a different thing. So let us see what is going to happen if I add one Sr. So if I add one Sr, what I have to do? I have to remove one of the sodium. So let me remove one of the sodium. Okay, let me remove this dash lines here. Okay, so if I want to replace, then I will replace one sodium and then I will write here Sr. Till here everything is fine, but let us look at the charge. So all the sodium are positively charged, one positive, but the Sr is what? Sr2 positive, right? Yes or no?
Yes, sir.
Yes, sir.
Now this is difficulty. We removed +1. We added, if we look at just from the charge perspective, we added +2. We added one charge and we removed one charge and we added +2 charge. Now this is going to create an instability, right? Electrical instability, yes or no? Tell me.
Yes, sir.
Correct?
Yes, sir.
Now in order to maintain the charge, see the charge should be maintained. Number of atoms kitna aur nahi ho raha, that is not a case. The charge should be maintained, and that is in order to maintain the charge, I have to remove another sodium positive ion. Yes or no? Tell me.
Yes,
Correct?
sir.
Yes, sir.
Now the charge is maintained, but as the charge is maintained, we have got a cation vacancy. Is that right? Yes or no? Tell me. Is that right?
Yes, sir.
Now the important point is there. Now you tell me, instead of Sr, if I had, let's say for example, if I had aluminium 3+, then I see in this Sr I have removed only 2 sodium and added one Sr2+, and I have created one cationic vacancy is created. One cationic vacancy is created. If I added Al3+, then I should be creating 2 cationic vacancy. Yes or no?
Yes.
Yes, sir.
Correct. Now you can see number of cationic vacancy. Number of cation vacancy कैसे calculate करेंगे? Is equal to the difference in charge. इसका mod ले लेते हैं. इसका plus minus नहीं देखना. You just have to see the magnitude here, है ना? Just have to take the magnitude. You will have in Sr you have 2 positive and 2 minus 1. NaCl has 1. If you mod this, then it will be equal to 2. Okay, the difference of the charge, sorry, difference of charges, sorry, 1. So the number of cationic vacancy will be for each ion. If I am doping with one molecule, then the number of cationic vacancy will be 1. Okay. So number of cationic vacancy is equal to number of SrCl2 added. Is this clear? Yes or no? Tell me.
Yes, sir.
And how many SrCl2 is added? So this is the wording here. Now this wording is a bit strange. You have to take this whole thing. So this is equal to 10 to the power minus 3 into mole, that is 6.022 into 10 to the power 23 into percentage. Percentage means what? Percent. That means per 100. Yes or no? Tell me.
Yes.
Is this clear? Please remember this point also. Sorry. I wrote all of those things, and all of those things will be vacant now. Arranged. Okay. इतना तो आपको पता चल गया था. This will be equal to number of cation vacancy is equal to 10 to the power minus 3 mole percent. So this will be equal to 10 to the power minus 3 into Na divided by percent is 100. So this will be equal to Na into 10 to the power minus 5. So yeah, 100 will go above. This will be equal to 6.022 into 10 to the power 23 into 10 to the power minus 5, which will be equal to 6.022 into 10 to the power minus 18. So this is the number of cation vacancy that will be present. Okay?
Yes.
I hope this is clear. Yes or no?
Yeah.
Okay.
Yes, sir.
So please write this down. You understood that part, na? That number of, we will लिख ही देते हैं इसको, लिख लीजिएगा, number of cation vacancy for each ion. This will be equal to the difference in charge. Okay. And in this case, it is equal to 1 minus 2 का mod, which will be equal to 1. वैसे आप लोगों को ये पता है, if you remove this mod, then you will get two answers. X will be equal to, if you have something like this, na, X can be equal to, if you have a variable here. So let us say this is equal to mod of X is equal to 1. Okay. अगर mod of X is equal to 1, तो X का value क्या हो सकता है पता है? X का value हो सकता है -1, and X can be also +1. Yes or no?
Yes. So because inside the value, value can be minus or plus.
ठीक है, तो वो वेरिएबल की केस में हो सकता है ऐसा.
So finished.
Done?
Yes.
Okay. Now I think if you look at this structure, this impurity defect, then you can easily see that we have one SR2 positive and there is one vacancy here. Okay, there is one vacancy here, and you also know why there is vacancy, because we need to stabilize the charge. We need to stabilize the charge. Is this clear? Yes or no? Please tell me.
Yes, clear.
Okay. So the impurities and the defect is done.